Up the final session with the second part of Daniel's talk on quantum many-body physics. In fact, the computational complexity of it. Daniel.
Thank you, Ashwin. And today I will want to talk about three things. First, what are all the different local Hamiltonians that we're interested in, the ones that are really difficult, but also the ones that are kind of easier. And then what are the ones where we have algorithms for them, and what are we doing in practice to find these ground state energies, focusing on mostly heuristics in the algorithms. And then finally, I'm going to ask the question of when we have these Hamiltonians, what are they used for? Can we use them to build a computer, or can we use to simulate one quantum system with another quantum system? So first, we start with a question about the local Hamiltonian. Is the ground state energy of some local Hamiltonian small? One thing that problems can be difficult, can be characterized whether their solutions can be efficiently verified on a classical computer or maybe on a quantum computer. So like a problem like this, you've got a Hamiltonian cycle, you've got a board, and you're supposed to make a tour of the board with a chess knight so that you end up at the same spot. And this is how you do it, and I just convinced you. Right? So it's easy. Quantumly, we have a quantum circuit, and I'm asking a question, is there a state that I can feed into this circuit so that the circuit will accept it? I need some ancillas in there, and the class QMA is the class of problems that have these verifier circuits, which accept good proofs with some high probability, and when they don't accept anything, then we have to have a bound that they don't accept anything with probability higher than something. Now, the local Hamiltonian can be shown that it's as hard as this problem. And this problem is really, can we feed something into the circuit so that it outputs 1? And the way that this is done is that somehow we need to encode a computation into a ground state of a Hamiltonian. Well, what is a computation? A computation is a sequence of steps that something is happening, and then a computation gets done. Classically, we can really verify every step of this computation in a simple way, like this. We have strings, and then we compute on the strings, and really something has happened, and we can verify that these bits are the same and these are not. And then in the next step, there's just like a little thing that has happened, and we can verify this. And this is the basis of the Cook-Levin theorem, where really you put bits on every wire in the circuit, and then you compare whether they're actually evaluated correctly, and you change it to 3-set. With local Hamiltonian, it's slightly different. The reason for that is when you have states that are quantum, you cannot really compare them. When they're product states, we have a swap test. So even if they're superpositions, we make a swap, and we can check that the state is the same, or we can swap different ones. However, if a state is entangled, it's a superposition of something that, like, for example, like a cat state 0, 0, 0 plus 1, 1, 1, and now we switch just one bit, we get a mess. We cannot really compare that these states are the same. So the way to solve this problem is when we want to compare two states which maybe differ only by a single spot somehow. I want to compare them locally. I need to get another register. The register will be called a clock. And then, for example, when the clock runs, something happens to my data. And now I can compare two states like these just by looking at the clock and by looking at the data. So for example, when the clock runs forward, something happens on the data. When the clock runs backwards, something is uncomputed on the data. And then I can look not on the whole state, which might be much bigger here and much bigger here, but I will just look at the one spot and at the clock. And if this is possible to do locally, then we can verify a step in a computation. So really, a computation quantumly is encoded in something like this. You've got a work register, this is where the computation gets done, and here's a clock register, something that kind of drives this computation. This was Feynman's idea, then used in Kitayev's proof of completeness of local Hamiltonian. And the great idea then is that you take a uniform superposition over the whole computation. And this uniform superposition is the history state, and it's a very special state which we can make into a ground state of a particular sum of many terms, and then this creates this local Hamiltonian so that we can write k-local conditions so that whenever there is a state in a particular state of a computation, then there needs to be the next state in the computation, just like the clock goes forward and the data gets computed on. And then there are more things that we need to do. You look, there's this clock register that I had just as a watch, but I need to do it in terms of like local spins or something. So you need to check whether the clock is proper, and then you need to check whether the state, for example, is a computation that is accepted. So you look at whether it's properly initialized, and you look whether it's accepted at the end. And this altogether gives us a k-local Hamiltonian for which we can have the question, is its ground state energy low whenever there's an accepted computation, or its ground state energy is high if there is nothing that the original circuit, which we're trying to check its verification on, has computed. The hard part is making the clock local and somehow interesting. Whole strategy is that in the yes cases, if we had a circuit that you could feed something in that the circuit would accept, the ground state energy would be low. In the other cases, if there's nothing that the circuit would accept, then we need to find a lower bound on the energy. And the way to do this is that we take the whole Hilbert space and we divide the Hilbert space into states that have clocks that are somehow proper and the clocks that are improper. Then we forget about that part. Then we look at all these states here that have proper clocks, and some of them are uniform superpositions, or like history states, and some of them are not history states. So we forget about these. And within the states with history states, the hard part, or something that I would like to get rid of, is that within that, there's the Hamiltonian restricted to that subspace, has a polynomially small gap that goes like 1 over L squared, where L is the number of gates. It's linearized. So I need to kind of like put all the gates in a circuit in order. And this Hamiltonian corresponds to quantum walk on a line, or maybe also on a cycle. So if we could get away from this, that would be nice. And then with the history states, you just divide it into the states that were properly initialized and improperly initialized. And then you've got the well-initialized histories that possibly might be accepted states or might not. These might be two different subspaces. And then in the null cases, when nothing is accepted well, so no well-initialized history and computation is accepted, then you need to find a lower bound on two different Hamiltonians, where one of them is saying, did we compute correctly? And the other one is, did we accept the computation? And there are geometric bounds that you can put in, and then we can go much more into the details. But in the end, this is the result. You have a circuit, and you ask, can I feed something in here that will be accepted? In the no case, the circuit doesn't accept anything likely. And it transforms into the local Hamiltonian problem, where any state has an energy that's higher than something. While if the circuit accepts something likely, then there is a state, the history of a computation, which is accepted, and its energy is low. One of the tools that's used there, that's very useful, is a projection lemma. So it's when you have a big term and that possibly has a ground space and a higher energy space, and you add a small term to that Hamiltonian, then the spectrum divides. And we know that the low energy states definitely need to come from this subspace. So we can get a bound on the eigenvalues of the sum of these terms by looking only at the small term restricted to the ground state subspace of the big term. So something just like this. So for example, if I have a term, the little term, it looks like this. And the ground state subspace of the big term that looks like this, that are unary terms, then really these interesting points will come only from transitions where the 1 gets transformed into a 0 here, or a 1 gets transformed into a 0 here from this term, and never from 1 going away here. This is one of the main tools that has been used in taking Kitaev's original 5-local Hamiltonian down to a 3-local Hamiltonian. And then there's much more that we need to work on, so that we take the 3-local interactions and we make effective 3-local interactions out of 2-local interactions. So you put in 3 more spins, and I want to have a 3-local interaction. And I make these 3 spins to want to be the same, either all of them looking this way or all of them looking that way. And if there's a small interaction here, the small interaction here, it's kind of this guy gets never flipped unless all of them get flipped, because they're so tight together. So in the end, these two will feel it. And all together, we will get an effective 3-local interaction out of 2 local interactions. However, what comes in there is just another energy scale that you really need these interactions to be way, way stronger. And altogether, this reflects in the promise, or like how, about in the question, how well do we need to approximate the ground state energy? So way, way stronger is like a polynomial. I don't know whether it's like L to the 3 or L to the 5 or something.
So it depends on the whole, because here on that picture
there's only one particular interaction, but in the end, if you want the whole construction to go through, you need these interactions to be as strong. It needs to take into account the whole computation.
So that's because in your previous picture you had the big Hamiltonian that has a certain gap, and you're adding the small Hamiltonian. Somehow the weights there need to be related to the gap that you had for the overall Hamiltonian.
Possibly, so that like in the very end, like we had some gap, and then like we added terms that could make a mess. So we had to make sure that whatever we're adding is just smaller than what we had before. So what has been done with this then is we have the local Hamiltonian problem where we're asking about the global minimum of many, many terms. The best result currently known is for two local interactions on a 2D grid by Roberto Oliveira and Barbara Terhal from 04 or 05. So this is two local Hamiltonian for qubits in 2D. Or two local Hamiltonian on a line, so just nearest neighbor interaction on a line in 1D where the particles have dimension 8. One of the problems that we really don't know the answer for is something below this. So for example, we don't know the answer to how hard it is to approximate the ground state energy of a spin chain of qubits. We don't know how hard that is. We don't know whether we can encode a computation with a quantum circuit into it. I don't really think so. Can we even encode a computation with a classical circuit into it? We don't know either. We know that when the Hamiltonian is gapped, we have an algorithm. We've heard from Zef about this. But what if it's just frustrated and we have no promise about the gap of the Hamiltonian itself? Then we don't know. Of course, you're going to hear a little bit later about the great success of the DMRG method, which really, the condensed matter people will say, like, we can solve anything in just 1D with spins, with spin 1/2. So I really want to turn our attention to problems that are somehow intermediate, that are not that easy. We don't have algorithms for them yet, but it's highly doubtful that we're going to be able to encode the full quantum computation into them. So problems that might not be QMA complete. And I'm going to give you a small example of something that I find interesting. But then also might be not just classical, but somehow naturally quantum. Also something that I would like to get away from is this clock work register construction. Could we get something else there so that we really are not bound by this 1/L² gap all the time? One way of also just not doing it just directly as a clock and work register is doing it with a geometric clock. That's in constructions by Ari Mizel and Dan Lidar, or for example in the universality of adiabatic quantum computation by Dorit and Zef and others, where we got particles that are kind of jumping down the grid, maybe together, maybe one by one, and really where the particles are, this is my data that runs through a computation, and as it jumps, it gets computed on. So this is a geometric clock construction. And also, yes, 2 days ago we were discussing whether something like this is on a general graph, where it's like really just anything connected to anything. It turns out that you can actually make these constructions so that they're really geometrically local, so that a particle is interacting only with a constant number of particles that are nearby and really nearby and embeddable in 3D space. And the way to do it is that, for example, this is your data, and the data kind of wants to jump down a grid, and the clock register can be wound around this physically, this way. So that, like, when you go this way, you compute, so as the clock progresses, like 1, 1, 1, 1, 0, 0, 0, and then when the clock goes kind of backward, then you make these particles jump in a grid. And then you do this over and over. And then every particle, like every data particle, is not like here is interacting with all the possible clocks at all possible times, but it only interacts with a few clock particles and only with another few data particles around it. So geometrical embedding into 3D with a constant number of things is possible. And finally, it is possible to do this construction in 1D on a line. This is what in my in talks I sometimes call it like the pick up a head, put it on your head, put it down on the ground, jump over it, and kick it back technique. So jump over head, kick it back, it puts it on the head, puts it down, and then goes back. And so the data, which here was moving down a grid, now the data is moving on a line. And if you look at it, really the rules, like what's happening, it's always only two places that are changing. And with something that's slightly more complicated, you'll get the Aharonov-Gottesman-Irani-Kempe construction for the power of quantum systems on a line. So I'm asking for a different construction, or possibly for problems that would have stronger promise on the, or that would allow for a stronger promise, so there will be larger gaps within the Hamiltonians themselves and a larger promise gap. Possibility of having non-trivial problems that are somehow intermediate, that don't really encode QMA. And then, of course, some other interesting hard problems. So that would not go directly from the translation from the circuits, something that I was talking about 2 days ago. One of the problems that, for example, we know that is difficult is the computation of electronic structure in quantum chemistry. So the computation goes like this. You've got electrons that are impossible in many orbitals, in a molecule that has lots of atoms, and then you need to fit them in there. The possibility for the orbitals, we know them from chemistry, that are all these like sp and higher, whatever. And then we've got many electrons that you need to fit in there. So that's like m orbitals and electrons, so there's possible m over n. This can be a huge number. So the whole computation can be really, if you do the full configuration interaction computation, which means that you really do it exactly, it's horrible. So we can really do it for very small molecules. So if we want to do this, one of the ways to solve it is something called the density functional theory. And it's instead of solving for electrons that are interacting, you transform your problem into another fictitious problem where you only solve for the electron density, and so where the electron actually don't know about each other. But to make this new fictitious problem is a hard thing in general, just because it's QMA complete, as shown by James Whitfield, Norbert Schuch, and Frank Verstraete. Because you can take, if you could solve this problem, then you can solve stuff with interacting electrons, for example, the Hubbard model. And with the Hubbard model, you can simulate the Heisenberg model. And with the Heisenberg model, you can solve the two local Hamiltonian, or they're progressively kind of weaker. So that means like you will not be able to find the density, the universal density functional. What about if we don't want to find it exactly, but we want to find an approximation? So for example, like with the Hartree-Fock method, that one is NP complete in general. So this tells you that like in the worst case, quantum chemistry computations are really difficult, but we really don't know how it is on average or in real life molecules. And again, maybe these will be instances of problems that might be doable. Like just when we talked about the condensed matter problems, where in general the problem is really difficult. But specifically, for example, here there are fields, external fields, which don't actually exist in the molecules.
Sorry, so when you say Hartree-Fock, is that the same as mean field theory?
Somehow.
Somehow, okay. Is it a heuristic or?
Oh, I don't know.
Okay, wait,
Another thing, that when you're solving for this electronic structure, maybe we're really wanting to, we're getting the wave function. But if you don't want the wave function, if you're just only interested in like reduced density matrices, maybe that would be easier. But we also know that this problem is difficult because this is related to the n representability. That like given a few reduced density matrices, does this correspond to a full state? And we know that one is also QMA complete by Ika Liu, Matthias Christendel, and Frank Verstraete. So let's go to the variants of local Hamiltonian. What are the ones that we can look at? First, stochastic Hamiltonians. Stochastic Hamiltonians are Hamiltonians where the off-diagonal elements have the same sign, or negative sign. Those are not universal for quantum computation, or at least we don't know that they are. But these are the ones that we can actually implement in superconducting architecture for quantum computers. Another one, and
sorry, is there a reason that it's easier to do those in superconducting qubits than?
I don't know whether
Or is it just
that there's a
the ones
reason.
that-
It's just really like, for example, you have a circuit, and you have a circuit, and then this one is making a magnetic field, and this one is registering it, so it's easier to make like a ZZ interaction. But to make an interaction that will be a Z and an X, while being able to do the other one is not that easy.
But if there's no fundamental
No, it's just we don't really know how. Like we don't know a physical realization. So in the constructions, in the practical superconducting architecture, we only have particular interactions that are available. And the ones that we've got are only the ones of this type, at the moment, I think. Second interesting subclass of local Hamiltonians are the ones with commuting Hamiltonians. That's also what Zef was talking about, where we have got the area laws and so on. They've been investigated by Bravi and Viali, which has shown that when you've got two local commuting Hamiltonians, the problem is in NP. When you're looking at plaquettes in 2D, so like you've got four things, so projectors or commuting terms on 4 spins at a time, it's in NP. When you've got 3 local interactions with qubits, Dorit and Lior have shown that it's in NP. When you've got Qudits and the geometry is kind of like planar and something special, it's also easy. One thing that I want to point out though, that the commuting Hamiltonians are not just something that's just really somehow classical. They really encode interesting quantum things because the commuting Hamiltonians are, for example, the Kitaev's toric code. Or we've heard from Ben Reichardt yesterday about stabilizer codes, where you've got, again, like terms that are commuting, and together their eigenspace creates a code. Another thing that's interesting about commuting Hamiltonians, that we've got the constructive Lovász local lemma, proved by Martin Schwarz and others, and by Itai and Orr from last year, where really we have an algorithm to find the ground state. But it's with the conditions of the Lovász local lemma, so that means if there are not too many conditions on each of the spins, and the conditions themselves are commuting, then there is a way to find the ground state. And the way really goes like the constructive Lovász local lemma classically, or like somehow like the Walksat algorithm, that you make a projection. If you succeed, you continue. And if you fail, you just take that away and put in a random state. And keep doing this. Keep doing this and keep doing this, and you will converge. If there are not too many conditions on each spin. But we really don't know how this works when you've got many conditions on each spin. We don't know how it would work for non-commutative ones. Really, there is a lack of a natural, even really badly scaling algorithm that will find ground states for quantum systems. Especially because when you're looking at something that's non-commuting, so for example, you check here that this condition is met very well. But then you check whether the next condition is met very well and it's not, and it can mess up something in here. You don't know which one goes first, which one goes later. It's a mess. Also, we don't really have algorithms that will work like this for even simpler problems. So there's an algorithm for quantum two-set by Sergei Bravi. That's classical. But when you try to do an algorithm like this, which like project, and if you don't succeed, do something, and if you project, and if you succeed, keep going, we even don't have an algorithm like that for full quantum two-set, which we know is easy classically. So Shelby Kimmel and Eddie Fari have been working on this, and they have shown that an algorithm like that works for just only a restricted class of quantum two-set problems. So there's a lot that needs to be done there, even for simple Hamiltonians.
Question?
Yes?
So when you're saying this constructive local,
Lovász local lemma.
yeah, so do you mean you have polynomial time and classical Emerson?
There's a polynomial time, it's a quantum algorithm. It's really, you project, you may have to make a quantum measurement. Okay. And then if you don't succeed, you have to put in a random quantum state on that subsystem.
But another question is how can you compare the conditions from this lemma to you have hardness result for MP, like still commuting the true local.
Mm-hmm. So how can I compare it to this result where we know it's commuting and it's in NP?
Yeah.
The thing is that here there's only few conditions, so it's a special condition on top. So every particle is interacting only with involved in only very few terms. So it's kind of like when there's few terms, something works.
Are you saying the hardness case for the true local NP hardness, they have a very strong connection?
It's general. There's no restriction on how many things you can be involved in.
But I'm referring, they should prove the hardness by really constructing something concrete, right? So in that concrete example, of course, if one should not satisfy the condition from this. I just want to see how what's the gap between those two.
I don't really know. Maybe you can discuss with Or, who was one of the authors for that, just to see what the detailed difference there is. Okay, so let's leave that for now. Another class is where you've got restricted terms, so only particular terms of Jake Belmonte and Peter Love have shown that when you've got xz and x and something, then it's universal. But now we've got the dichotomy theorem by Toby and Ashley, where it's shown that like particular terms, everything's easy. If you've got these types of terms, this problem really is like a two-local Hamiltonian. It's as hard as that, and it's difficult. And then finally, there's a variant where we've got a fixed interaction, so the same interaction between the particles, but the interaction graph is different. And this is the most recent result about the QMA completeness of the Bose-Hubbard model by Andrew Childs, David Gossett, and Zach Webb. Another variant is a variant without frustration. So that's a quantum K-set problem by Sergei Bravi. So imagine that you don't have terms and you're asking for a global ground state, but you've got projectors. This is my Hilbert space, and I'm projecting stuff out. I'm projecting, and I'm asking, is there a common ground state of all of those? So is there anything left after I project out with all of these projectors? Is there a state that's simultaneously killed by all of them? This is quantum K-set. So this is really like an analog of set, classical set, while the local Hamiltonian is analog of max set. And the result here for the unfrustrated set is that when you've got two local interactions between 5-dimensional and 3-dimensional particles by Lior Eldar and Oded, this is QMA1 complete, because you can really certify things, because you have to exhibit a state where it really is killed by all of these projectors. And on a line, you need 11-dimensional Qudits on a line. But how does it look when you've got unfrustrated problems in smaller dimensions, so really just not spins, but Qtrits? This is something I'm interested in. And also, like when you've got 3 local interactions of qubits, so this is the quantum 3 sum, this is the recent result of David Gossett. Another question that we can look at is random quantum sets. So just like classically, we can look at random instances of satisfiability. Then we just put, if we don't have many conditions, the instance will be satisfiable. And you can put in more and more projectors, and suddenly the instance becomes unsatisfied. And what we have realized, that when you have quantum set, this is the number of solutions, there are definitely parts that are like classical instances and quantum instances. And classical instances have more solutions than the quantum instances. So we can actually show that when there's a particular classical instance on a given graph that has no solutions, it really means that the generic quantum case is also unsolvable. So we can bound quantum set by classical adversary set. And this is work from Antonello Scarnicchio and Marco Bardoscia from we did last year. I want to focus more on one dimension. So what happens in one dimension? In one dimension, you can have local Hamiltonians whose ground states are uniform superpositions of things like what I call surfers on a domain wall. So here spins up, spins down, and here's a surfer that rides the wave. And a uniform superposition of these is the ground state. And it's not very entangled. It actually has Schmidt rank 2. And you can do this with a 2 local Hamiltonian on a line with Qtrits. But you can do more than that on a line if you increase the size of the local particles. And that's the power of quantum systems on a line result by Dorida Arnaud, and Daniel Gottesman, Sandy Irani, and Julia Kempe. And there it is, the thing that I showed with the hats, that you've got some part of the chain that kind of encodes the data, and the data can possibly move. The data moves forward and then jumps over something and moves forward again. And as it moves forward, then a computation can get done on the data. And again, the data will try to move a little bit to move forward, and then a computation will get done somewhere later. And all this uniform superposition over all these things will be a possible ground state of this local Hamiltonian. And we can show that if this state exists and has a low energy, it corresponds to an accepted computation. So again, the problem with 13-dimensional particles on a line is QMA complete. So with nearest neighbor interactions. And the ground state is entangled because when I make a cut, these are basically like the states. This is like a Schmidt basis. And there's even more, like I need to really divide this because this could be a very entangled state. But also when you run, instead of a quantum verification, you run an NP verification, a classical circuit, then these things are not very entangled. But altogether, there is a polynomial number of states here in the superposition because there are all these states where the computation is gone, all the states where the computation is not have been there yet, and these like polynomial in n states in here while the computation is running through this cut.
Could you say again how this problem is different from the one for which d equals 8 is QMA?
So for 8, is that there we have, here in this particular construction, there are no illegal transitions, which means that we have stronger promises, and the problem could possibly be unfrustrated. While with the 8, we're introducing these bad transitions and things that when you do the analysis of what's happening in the dynamics, it's not really a walk on a line. It's a walk on a line and like possibly some jumps away. So you have to be much more careful. So we are.
The formulation of the problem is a different promise.
A different promise. So you need a stronger promise.
In this case.
Sorry?
A stronger promise in this case. We have to go to
higher precision for the d equals 8. Yeah. So this is you can trade parity for local dimension and go down to 11. I've shown this in 2008. And then really with Sean Halgren and Sandeep Narayanaswamy, we have shown that you can go down to 8-dimensional particles and the problem still stays QMA complete, but now becomes frustrated. So you need a better precision. Or the question is, is the ground state energy lower than this or greater than this with a much smaller promise? And this construction has been then used for this translation invariant Hamiltonians, where somehow you have a grid on which you can have a computation that runs and writes down what the computation is doing, that it writes down the size of the grid. And then you've got a second layer of computation that takes down that number and does a computation that's encoded in this number. So you run a universal Turing machine on the program that the first machine has done. And this is done on a big grid, depending on how big the grid is. That computation you will run. But when this really needs huge qubits because there's like 2 layers and many possible states and this number is multiplied there. And then what's also important there, it's not really when we say that translation invariant Hamiltonians are QMA complete, it's not that simple. It is that QMA X complete. So you've got like an n times n grid, then you can run a computation of size log n. And this is all in general in the worst case. So when I ask you the question, what is the ground state energy of a translation invariant Hamiltonian for qubits or spins 1/2 on a 2D lattice, this might be easy. Really the problem that we know is hard is that when there are exponential size lattices and the local dimension is very, very high.
Has anyone tried to estimate how large the local dimension has to be?
For this one, I don't think they even did that, but it's a lot. Could be brought down. So let me just tell you about the local dimensions in 1D. So when we do something with 1D, we know for translation invariant states with 21-dimensional, or maybe I brought it down to 14, is that you've got very entangled states for unfrustrated ground states in 1D. With 11, you can do quantum computation, or it's QMA1 complete. For 4 dimensions, it's very entangled. For 8 dimensions, frustrated, it's QMA complete. For 2 dimensions, so that means for qubits, the problem is easy because there are always product states that are ground states. And for 3, we have found something there for Qudits. So when you have a Hamiltonian that's on a line, nearest neighbor interaction, and I'm asking, is there a state that is killed by all of these terms? Is it any interesting? Is it hard to find it or not?
So, sorry, don't you need large entropy to get QM completeness?
Yes.
So, sorry, your bounds there are higher than for QM completeness?
So here, we're finding a state that's not that entangled. It's somewhat entangled.
No, I meant,
But here,
yeah. So
this is like... this is
Or
a
is it translation?
this is translation invariant. Yeah,
Okay.
the distances here are the same. So it's a particular Hamiltonian that has the same interaction everywhere, and the ground state is quite entangled. It's not as entangled as it could be. Yeah, that's a good catch. So here, the entropy will be much bigger. So this is a suggestion. Why don't we look at Qudits? For Qudits, like this is a bracket construction that.
What did you say about the entropy
Here?
going log out? Yeah.
So this is something that's like indicative of a critical system where the entropy goes like log L.
Yeah.
But we can make a construction when we have a Hamiltonian that's unfrustrated, has nearest neighbor interaction, has a unique ground state that's that entangled. So the way to do it is that I've got 2 local terms that allow for brackets to be created on a line, brackets to move around on a line or just disappear. And the ground state of this Hamiltonian is a uniform superposition over all well-bracketed words. This is how the ground state looks like. So it's not a computation in a circuit, but it's just a superposition over all well-bracketed words. And this is a Hamiltonian that is an unfrustrated ground state. It's unique, quite entangled, and it's protected by a 1 over polynomial gap.
The surprise is that it's unfrustrated.
The surprise that it's unfrustrated, yeah.
And we knew there were critical chains. Even
Definitely. Definitely. We knew critical chains that have this type of scaling, but this is unfrustrated. And you would think that unfrustrated problems are somehow easier.
So what does it mean to be critical?
So critical classically means that like you're changing parameters and like everything is easy, correlations fall down exponentially, and then you hit a spot where suddenly the correlations blow up or would go, like the correlation length becomes infinite, so like really this part of the system is correlated with this part of the system, so you expect that you really need a matrix product state with a large dimension to describe the state. So for example, here we really need a matrix product state with only polynomial dimension to describe this state. We actually know what that is. But this is without any like change in parameters, this is without, generally you have a phase transition when there's a competition between 2 types of interaction terms, so some kind of frustration, and we don't have any frustration here. So I'm suggesting let's look at things in lower dimensions. So this is for Qudits, for something where we can encode not a full computation, but maybe a weaker model. So here the model could be possibly push-down automata. So like you can encode all the things that you can calculate with push-down automata within the ground states of Qudit chains. I don't know whether this is true, but I'm looking for something like this, possibly. Because we don't even know whether we could encode something that's like a classical computation in a spin chain, spin 1/2 chain. Okay, let's change gears now and turn into the algorithms that we've got. So really to find the ground states of local Hamiltonians. So I've shown that we've talked that we have the algorithm for 1D gapped spin 1/2 chains. Or is it also only for spin 1/2 or is it for higher as well? Higher as well. Okay, so just 1D and gapped. We have an algorithm for quantum 2 set, and we have an algorithm for a quantum algorithm for an almost independent commuting case, so that a particle is not involved in too many. But that's all. These are provable. And then we've got lots of heuristics. We've got lots of letters in there, and I'm just going to explain about what they do, because this is what we really do in practice. Because the condensed matter people want to investigate, the quantum chemists want to investigate their systems. So what is it that we actually are doing, even though we know that in the worst case the problems are ridiculously difficult. So for example, what is the DMRG? I've got it. This is my possible basis. So this is a computational basis state for spins 1/2 on a chain. But instead of looking at the full basis, let me just divide the system and like look at a like left part and a right part, and then just a single spin. And I have the full basis. But let's not work with the full basis. Let's just make a smaller basis and choose just D states. And let's try to find something within this ansatz. And the way that we're going to do it, that if I choose just D states, then each of these states has some cost. Like maybe this one, like when it interacts with the spin up, it will raise the energy a little bit. And when this one interacts with the spin down, well, the energy will go down a little bit. So we try to do our best within a basis. So you've got these prices for these basis states, and we try to combine them. So for example, if there's a Hamiltonian term that interacts like this one with this one, so we put these things down, and then we make an effective Hamiltonian within this basis. Then we solve it, and we really find the best state. You do this with the Lantos algorithm, because this Hamiltonian could be sparse. And the very important thing is that you don't really actually calculate the Hamiltonian, but you only, in the Lantos algorithm, you need to calculate, you take a vector, and you multiply the vector, and multiply the vector. You never really make the matrix. Yep?
Can you do this again? I'm sorry, but
Yeah.
I did not get anything of this picture. So price is what? Is the energy?
The price would be like the price for a particular basis state would be that, well, what's the Hamiltonian on the first Hamiltonian 1, 2 plus Hamiltonian 2, 3 plus Hamiltonian 3, 4 that are not involved in anything. That basically like it's the energy of the left state.
So your little block there, that's light green or whatever. It's what? It's a quantum state.
It's a quantum state
On the whole system, or
on the left part of the system. But it's a particular state that I choose. So I choose that. Let's find out what's the best state that we can find if we can do whatever on the middle spin, and only these possible states on the right side, and only these possible states on the left side.
okay.
So with a restricted basis, within some ansatz.
Okay. So you have a polynomial number of stuff.
Yeah, definitely. Like we choose d of those, like some number. Really, in practice, we choose 1,000.
Okay.
So instead of like 2 to the size of the left part of the system, you choose just 1,000 states.
Yeah.
And which 1,000? I mean,
So that's a question. You start with, really somehow on the left, and you choose like spin up, spin down. Then you make a next step, and you need to choose something from 2 states. So you still choose 4 states, and you keep going. And at some point, you have to start throwing stuff away. And I'll tell you how do you throw stuff away. So within a particular basis, we make an effective Hamiltonian, and then we find the best state with what we've got.
Sorry, and what you keep on the right?
So on the right, it's again some list of states that I have gotten from before.
Yeah, so on the left you started with everything and you kept throwing out, but on the right,
I'll
presumably that's
tell you. So I'll tell you now that you give me states, and I try to find what's the best that I can do with them. So you do your best, and then I ask, the state that I got, is it very entangled or not? So I do a Schmidt decomposition along this line. So I do a Schmidt decomposition, so now these states become orthogonal now. And you do the Schmidt decomposition by just doing like a reduced density matrix of a subsystem and really diagonalizing it. So this is a Schmidt decomposed best state with the best that I've got. And then I just truncate the state, because like, look, these things are small, so I forget about some of the states in here. It's still a pretty good state, and really what's been left, it's still a pretty good basis. This is a pretty good basis for the left part of the system, and it will be a pretty good basis for the right part of the system.
Do this a few times, not just once.
So I will show you how you do it a few times. So really what has happened, that instead of having the states that you gave me and my particle, I now have the new states, new basis that I have chosen for your part plus the particle. So I have grown a block. And I will call this the new basis for this part.
So these
choice, you're disregarding the interaction with the right side.
I'm not disregarding interaction altogether. I'm just disregarding some part of it, like the ones where the left is not very entangled with the right. So the terms that are just very small. So I'm expecting only a few terms to matter.
But when you grow it by one particle, you're not, you're not taking into consideration the interaction of the particle with the right side. It's only with the left.
When I'm growing the block, there are particular things that are corresponding to this on the right, but I'm actually not going to keep them. So in the moment, I'm only interested in like how the left basis is changing. So I got a new basis on the left, and then what happens? I will recalculate like how much this new basis costs, the effective Hamiltonian for the left part, and then I will put in a new. I ask you for a new basis of one less particle on the right, put in a new spin, and continue. So then I will again find the best with what I can do here. This was new, this was old. Let me just show you graphically what's happening. Imagine that I start with 4 particles, and then I will recalculate and find the best bases. I will push them apart, try to put in 2 new particles in, recalculate. Then I'll get new bases for like the left part and for the right part. I can push them apart like this. This is let's do this for a translation invariant system. So this is how I can grow the system up, grow the system. And now I start something that's the build part, and that's called the sweeping part. That I have done, let's do the best within this basis and find a new basis for that part of the system. And then I call these guys and put them here and try to combine them. And I put 2 new particles in and try to see what's the best that I can do within this basis. I basically do the Schmidt decomposition here, throw off some terms, and only leave like what's useful for this part. And keep going to the right, and I'm making new bases for the left part. And then I do the decomposition here, and now I grow from this side. So I'll make a bigger list of bases here, and I will use up an old one from there. And you keep going like this in the system, there and back, sweeping around and leaving behind you stuff that you have just calculated. And this is an iterative process that allows you to find very, very good approximations to the ground states, but also to excited states of local Hamiltonians in a line. Really, what's the success? Is it that good? A critical benchmark would be a critical system like the antiferromagnetic Heisenberg chain. And when you take like 100 spits on a line, you take 300 basis states, you keep 300, you do just one sweep there and back. This all happens in minutes. Then you get like error that's 10 to the minus 13. It works fantastically for the worst systems that we can imagine.
Is the algorithm randomized, or when you choose these base states on both sides, is it deterministic the way it?
So in the beginning, it's deterministic. Yep. So in the beginning, it can matter like what you start with. So for example, one of the good ways to start was try to build the system up, not just start with a completely random state, and then start sweeping. So it helps to start smartly. And it also really helps if you also take some physics into account and if you know that your Hamiltonian has some symmetry, so it really divides into block diagonal structure. So you don't really need to do everything in.
So this 10 to the minus 13 error, is that for a solved model, or how do you know that this is how?
So we know that it's for the solved model, and then we know the convergence, that we know how much things are changing, how much the energy is changing when we're making the matrices bigger and bigger. So you can do the computation in days, and you can put tens of thousands, and nothing is changing.
But
so we conclude that the energy has converged.
How do you know you're coming to a ground state rather than some local optimum?
Okay, again, we test it on the systems that we have exactly solved, and we test it against systems where we have other numerical methods. And really, the stuff that we're getting by this heuristic is the best precision that we have. So right now, other things are tested compared to this at the moment for one-dimensional chains. It gets harder when you get bigger spins. So for example, in the Hubbard model, when you've got fermions that are interacting, so you can imagine that you have like 4-dimensional particles at each side, so then it gets harder and it gets slower. or when the geometry is non-tree-like, and also it converges slower when you have open boundary conditions. So really, like the boundary somehow matters. So you have to like go to one boundary, carry stuff to the next boundary, and keep going a couple times. This gets slower. And we know that when the spins become really big, we know that when they become like 8-dimensional, this is a QMA complete problem. But for spin 1/2, it's working great. For like 3-dimensional particles, it's working great.
Excitations?
Okay, so with excitations, so here when we were looking for the best that we could do within a basis, but we can also choose like let's keep the best 5 states within a given basis. So you can keep, you don't have to just look at the ground state, you can have several states.
But you look at only the bottom few.
Yeah, only the bottom few, exactly. That's what is interesting. So a good review is we show like DMRG in the age of matrix product states. You can look at that. One thing that you were asking also in the lectures before is that what happens when we do something not on a line. So when I have like a 2D grid, you kind of like thread a line through it, but then you see that like you keep like this is just one block, this is another block, and these are the 2 particles that I'm looking at inside. But really these guys could be very correlated, so somehow you need to carry the correlations all through it here. So you have to keep a lot of states so that you capture that. So for example, what's done, it's possibly stuff has been calculated on cylinders that are very long, but really like this diameter is, or circumference is small. Like on a Kagome lattice, that's really something that appears in condensed matter a lot. And what's been calculated that you see that the number of states that you keep is 200, 600, or 8,000. And you start with some assumption that this is on this lattice, that you're going to get something like a hexagonal valence bond crystal, that like these things will appear. This is how the spins like each other, or like how much they appear in a singlet there. And then when we increase the number of states, we realize that it goes away. And what shows here is something called a spin liquid. This is a recent work by Jan Hus and Webb. And what happens when they did this, the energy like goes down, goes down, goes down, and then at some like 2000 it jumps a lot, and then it stays, and nothing is happening. So sometimes you need to go to really high numbers, but then if it doesn't change for a long time, you conclude that it's converged. But again, this is not rigorous, but it is very useful.
Sorry, what were the numbers again?
The numbers are the number of states that you're keeping.
You mean the bond dimension?
The bond dimension. Oh, well, here it's, in matrix product state, it would correspond to the bond dimension. Here it's the number of states that I leave. Yeah, it is this bond dimension. For MPS, the way to do things is a variational matrix product state. So this is the picture that Zef was showing. That you've got a matrix product state, and I want to calculate the expectation value of a Hamiltonian, something that I want to minimize. So for example, when these 2 particles are interacting, I need to sum this up. These 2 particles interacting, I sum it. I need to sum this network, and so on. And I want to see how well I'm doing. Altogether, all these summations, in some way, they're creating like an effective Hamiltonian. And I need to divide this by the norm of the state. And I'm looking for the best possible matrix here. And this is doable numerically, and then you sweep, you keep going, like let's optimize this guy, let's optimize this guy, keep going a couple times, and you've got the best MPS that you can get numerically. And it works, for example, in quantum chemistry computations, either with DMRG or with the matrix product states. This is what Garnet-Chan's group is doing, or what Valentin Murg and Urs Legeza are doing in Vienna and Budapest. So there it is that you've got electrons that are supposed to be in different orbitals. So you can imagine how the orbitals could interact. So you've got some interaction between them, and you need to find the best association of like which orbitals are occupied and which are not. And there could be entanglement between these things. And you don't do it on a line, but you instead of these are the different possible orbitals that could be occupied or not, and you spread them and make them interactions like on a tree instead of threading a line in there. And somehow the effective distance from one place to another is just like log size of the.
So this is some another problem you're describing of optimizing the Hamiltonian, or what's the problem you're describing now?
So this is now, I'm trying to find the ground state energy of a Hamiltonian that involves interacting electrons. It can be translated to the local Hamiltonian problem. It can be translated actually into the four local Hamiltonian problem, exactly.
So the chemists have done that for us. And then
The chemists have done that for us. They have calculated the coefficients, and now we are applying this machinery to this four local Hamiltonian problem. And the machinery that we apply is just not direct matrix product states, but three tensor networks. And it is what I wanted to show. Just when you put like 16 bond dimension 16, then the error goes down. Like again, you get like 10 to the minus 14 for a benchmark little small quantum chemistry system.
Sorry, can you go back one slide? I'm not sure what's the relation between what you've done earlier in DMRG and here it seems like you're optimizing over all MPS states.
Yeah.
And either a connection between these two, like how do you optimize over an MPS? Is it related to DMRG?
So here it's like I have lots of matrices, and right now I'm optimizing one particular one, and I move to the next one. In the DMRG, this thing is not seen, the internal structure is not seen. It's seen as a big block. And with this summation, like for example, like this summing, this term is involved in the cost of the left block that we were talking with Thomas about the price of the left block. So here in matrix product states, you can calculate everything. You've got these matrices. In DMRG, you've got the thing together. You don't see this line. You see just a big block. But they're very related.
So can you just explain how variation on MPS works in a more detailed?
Okay, let's do that, and let's end the talk here. So the Hamiltonian has terms that involve particular spins. So spin 1 and 2, spin 2 and 3, spin 3 and 4, and so on. So to calculate this from here, I need to sum all that. So when you think of it, it's just as a formula. So it's a formula that it's some big tensor and then twice the little matrix. Because it's linear. It's just sum of a lot of terms. Okay, so this is this. And this might not have been normalized properly, so I need to divide it by the norm. So you need to minimize this. And way to do it is that you put in there some lambda, you differentiate with respect to this, and you get a linear equation that's a generalized eigenvalue problem, something like this times that is some matrix times this, and the energy. So it's possible to do it. Okay, there's plenty more that we can discuss with the people that stayed here, because I actually didn't even get to my third part about like really how well these things are doing, how you contract PEPs, and then possibly what you can do with the computer as a simulator. So let's just end up here. I wanted to show you the different variations of the local Hamiltonian, and I want to turn your attention to the possibly intermediate ones. I tried to give you at least a hint of what are the algorithms that we're using in practice, and also tell you that we really don't have many where we know that it works. I would even want a very good one, or maybe not a very good one, just an exponential one, a quantum algorithm for finding the ground states of local Hamiltonians, besides just Grover's search or phase estimation. So something different, something that will be more natural. And then that's a topic for the whole different talk, or I'll just let John Prexel continue with like how do you simulate stuff with Hamiltonians, or how do you simulate Hamiltonians. Okay.
John.
So, there's this paper recently by Matthias Treuer and co-authors, in which they are rather pessimistic about, well, I wasn't talking about that one.
Okay.
I'm talking about the one about quantum chemistry. Mm-hmm. And they're rather pessimistic about using quantum algorithms to compute the ground state energy of a large molecule, because they say, although it's a polynomial algorithm, it scales like the number of orbitals to the 9th power. guess the question is, do you think that it's just that, we need to optimize the algorithms and to get a better scaling, or do you think there's some fundamental reason why we will be stuck with polynomials, but
With a huge polynomial.
scaling polynomial algorithm?
So is there a reason that we will be stuck with a very badly scaling polynomial algorithm for either in quantum chemistry or maybe even like in contracting PEPs, like the infinite PEPs, the best algorithm we've got, like I think something goes like d to the 12, and in the chemistry would be d to the 9. So again, we know that in the worst case, it's terrible. We might find something that's better. I don't see really a fundamental obstacle. Of course, like there are little things like in the chemistry. So there's been this paper where they did something with just 2 photons, and they calculated the energies very precisely for a hydrogen molecule, and they did it with very, very high precision with iterative phase estimation. And this is the proposal that how quantum chemistry could be done for larger molecules. But for that, you really need like many, many more things. And for the phase estimation to go to higher precision, you really need to make many, many, many terms. So maybe something better can be done, but I don't know. This is probably like the best proposal that we have now. And even for contracting these tensor networks, for contracting these PEPs, there might be more clever methods that we just haven't figured out. There are ones that we do, like make a cluster, then do something within the cluster, and then continue. It's not easy. Like for example, for the matrix product states on a line, it's easy to contract, but things are far apart. When you make it on a tree, it's harder to contract because suddenly you have tensors with more indices. But maybe smaller indices, like smaller size of the bond, is enough. And there's a trade-off between that. And we need to find the best spot.
Yeah, so you sang the praises of DMRG nicely, but it's heuristic, so it must fail on some cases. So are there certain 1D systems on which it does poorly?
So are there some 1D systems on which DMRG does poorly? No, like the worst case are the critical systems that we know, and there it converges slower, so you really need to take more states, or just even the diagonalization, like finding the best state when we form the effective Hamiltonian takes longer. Just that itself, that's the longest step, but it still works. Like we get stuff with very high precision in minutes or in hours on today's systems. So really, I think like that I conjecture that the really hard ones would come from higher dimensional particles. So once you get to like Q quarts, Q synquids, or Q athids or something. Maybe not for just spins 1/2.
So it's conceivable that it is a real polynomial time algorithm. It's
No.
not just
So it's known to be, it's known not to work for certain one-dimensional systems.
Okay.
But for spin 1/2?
I don't know if it's for spin 1/2. It's certainly for one-dimensional, not necessarily two-state systems.
Yeah. So this is something that we know. Like for example, for the one where we can do the MP computation with Norbert's thing.
I see.
Maybe in the interest of doing justice with John's talk, we could postpone any further questions until lunchtime. Let's thank Daniel again.